So we started chapter 16 where we were talking about these electrophilic aromatic substitution reactions. These are reactions using our benzene ring, and we're substituting a hydrogen on there for some electrophile. Right, so this is our generic reaction mechanism. Here we have some electrophile. Benzene's then attacking that electrophile, so benzene's playing the role of the nucleophile. But when it does that, it generates this carbocation here and ruins the aromaticity of that ring. And benzene loves its nice, stable aromatic ring. So the last step here is to reform that aromatic ring, having that pair of electrons that was in that carbon-hydrogen bond come down to reform that pi bond. All right? So benzene gets to stay this aromatic compound in these reactions. And we have 6 such reactions that we discussed. Okay, where we're adding 6 different things to that benzene ring, or not really adding, we're substituting, but nonetheless, right? So we have these 2 halogenation reactions. We can add a bromine or a chlorine to the ring. We have this nitration reaction where we add a nitro group, or a sulfonation reaction where we add this sulfonic acid group. And then we have these 2 Friedel-Crafts reactions that are creating a new carbon-carbon bond, one of them between the carbon on benzene and an alkyl group, and the other a carbon on benzene and a carbonyl carbon in what's called an acyl group. All right? So what we're going to do now is we're going to take those 6 reactions and we're going to start mixing and matching them. All right? We're going to start combining these EAS reactions. All right, so first, let's just kind of practice, see if you can from memory here, tell me what we would do in each of these 2 reactions. We're going to take a benzene ring, and we're going to add, in this first instance, we're going to add nitric acid and sulfuric acid. All right, and in the second instance, we're going to add bromine and aluminum bromide. All right, and I'm just going to note I drew these 2 different ways, one where I stacked them on top of each other, one where I listed them in this comma-separated list. It's not like one's correct and the other's not, right? So it's just kind of a space-saving thing to stack them on top of each other, but you might see them listed next to each other too. It doesn't mean anything different. All right, so in this first reaction, I'm substituting my hydrogen for a nitro group. That nitro group is NO2, right? We start out with nitric acid, HNO3, but as we showed in our mechanism when we were showing how this electrophilic species forms, you lose one of those oxygens to become that nitro group. All right, and then in this adding bromine and aluminum bromide, I'm going to substitute my hydrogen for a bromine. Okay, great. Cool. So if we do just one of these EAS reactions, we're going to substitute a hydrogen onto that ring with one of our electrophiles. All right, but now what we're doing is we're going to combine these. So I'm going to do first that nitration reaction, and then I'm going to follow it up, and actually I'm going to sort of draw this out the long way here just to kind of prove a point. We're going to do this nitration reaction first, but then we're going to do a second reaction, taking that product, and we're going to do a bromination reaction. All right, and as we've established, that bromination reaction will substitute a hydrogen for that bromine. But now we have these different positions relative to that nitro group. We have these positions right next door. What do we call those? Ortho, meta, para. Ortho positions, all right? What about one removed down here? Meta, and then the opposite side of the ring? Para. So I could get either the ortho, the meta, or the para product depending on where that bromine's going to go, all right? And so what we're going to see is the order in which you perform these reactions are going to matter in terms of dictating what your product is. It turns out that if I do this nitration reaction first and then my bromination reaction, I will specifically get the meta product. All right, and just to sort of be clear here, we did that nitration reaction first, and then second, we did this bromination reaction. And if instead I did the opposite, I took those exact same two reactions, but I did them in the reverse order. All right, so now I'm going to do my bromination reaction first, giving me bromobenzene. But then I'm going to do my nitration reaction second. It turns out that we get a different product. We would get a mixture of the ortho and the para product. All right, so let me just draw these down here so I got a little bit more room. Now I get a mixture of that nitro group in the ortho position and in the para position. All right, so same two reactions, but the order in which we do these reactions is going to determine what our product is. All right, again, we took the same two reactions, a nitration reaction and a bromination reaction. Turns out if we do the nitration reaction first, we get the meta product, and if we do the bromination reaction first, we get the ortho and the para product, a mix of the two. All right, so what's going on here? Why is this leading to these different products here, even though they're the same two reactions? All right, we got to go back and have a discussion, something we've already sort of talked about a little bit before, these electron donating and electron withdrawing groups. All right, so let's talk about electron donating groups first. Okay, so first of all, we call them electron donating groups because these are functional groups that donate electron density. All right, and in this case, previously with Diels-Alder reactions, we were talking about donating electron density to those conjugated dienes. Now we're talking about this aromatics chapter. So we're talking about donating electron density to our benzene ring. I'm going to leave a bunch of space up here for some more notes about electron donating groups, but I'm going to go to the bottom now, and we're going to just look at an example. All right, so a good example of a benzene ring with a electron donating group would be this guy here. We have a special name for this guy. What do we call this? Phenol. So this is one of our special benzene derivatives. It's got its own name here. So this is phenol. All right. And again, what this hydroxyl group is going to do is donate a pair of electrons to this benzene ring. All right. If we're going to show that with our electron pushing arrows, that would look like this, where it's donating a pair of electrons to that ring. Okay, now I couldn't stop there without breaking that carbon's octet rule. So remember, these allylic lone pair resonance patterns require two arrows, one that pair of electrons coming down, and another with that pi bond pair jumping up onto that carbon. So everybody's going to take a second and draw me my other resonance contributor here for phenol. right, this first arrow here, bond breaking or bond formation. Bond formation, we're starting at a lone pair, that pair of electrons coming down to form a new bond. And then this one, bond breaking or bond formation. Breaking, so that means that bonding pair is going to become a lone pair on this carbon right here. All right, if it's a lone pair on my carbon, that's a carbanion, so I need that negative charge. And what else am I missing here? Positive charge on that oxygen. Cool, so this is this resonance contributor I get from that electron donating behavior of that lone pair. And we can keep going, right? Now we have another allylic lone pair. So we can keep on just bouncing this lone pair around this ring, right? It'll come down here. This pair of electrons jumps up onto that carbon. All right, so we got two more resonance contributors. I want everybody to take a second and see if you can't draw me the structure of those two resonance contributors. All right, so similar to our Diels-Alder reactions, we're going to be using these resonance contributors to try to understand the regioselectivity of these reactions, why we would get ortho-para sometimes and meta other times, all right? So that's what we're going to be using these for here. And remember, it's not that any one of them is true at a given moment. They're all true at the same time. So what this means is that when we're looking at a phenol molecule, what we really want to picture is that there's this extra electron density that's being bounced around this ring. All right, but let's note, it doesn't sit on all those carbons equally. That extra electron density is specifically in which positions? The ortho and the para positions, all right? So when we look at this molecule of phenol here, what we want to imagine is that these ortho and these para positions have this extra electron density. All right, that's what our resonance structures are showing. We have extra electron density at our ortho and para positions. Okay, so how does this explain what we observe in our reactions? Well, first of all, let's think about it. What role did we say that benzene was playing in these EAS reactions? It's playing the role of the nucleophile, right? And we also said that an electron donating groups adds electron density to that ring. So is that going to make benzene a better nucleophile or a worse nucleophile to have more electron density? All right, what are nucleophiles? The electron-rich ones or the electron-poor ones? The electron-rich. So if we make that benzene ring even more electron-rich, is that going to make it a better nucleophile or a worse nucleophile? a better nucleophile. All right, so these electron donating groups, we call these activating groups. All right, because by donating electron density to that ring, we make benzene a better nucleophile. All right. To be clear, that means that if we used phenol instead of benzene, it would react faster. Right? Even better nucleophile than if we just had benzene all by itself. All right, and looking at our resonance structures here, we're said that we're making this benzene ring a better nucleophile. But specifically, at which positions are we making that benzene ring a better nucleophile? The ortho and para positions. All right, so that's why these electron donating groups, we would call them activating groups, and we would call them ortho para directors. All right, they react faster than benzene all by itself, and they will direct incoming electrophiles specifically to the ortho and para positions. All right, and I'll talk about how we spy electron donating groups here in a second. All right, for right now, we're just going to take this one example of phenol. Phenol with that lone pair right next to the ring, it can donate that electron density. That electron density gets passed around that ring, but specifically at the ortho and para positions. That makes these electron donating groups ortho-para directors. Okay? All right, so then what about if we had the opposite? What if we had an electron withdrawing group? All right, these are going to do the exact opposite. Now they're going to pull or withdraw electron density from that benzene ring. All right, again, I'm going to leave some room, and then towards the bottom, I'm going to start giving an example here. So let me just take a benzene ring. Okay, and just like we saw for our Diels-Alder reactions, our electron withdrawing groups, a good example is a carbonyl group. All right, unlike phenol that was pushing electron density into that ring, benzaldehyde does the exact opposite. It pulls that electron density away from the ring and onto that oxygen atom. Okay, so that means that we're not bouncing a negative charge around our ring anymore. Now that negative charge has been pulled onto that oxygen. Come on. Oops. And we have this positive charge that's bouncing around our ring here. All right, these allylic carbocations were another one of our resonance patterns. And similar to before, can bounce that positive charge around the ring. So everybody take a second. We got 2 more resonance contributors you can draw me here. Oops. All right, and just like before, we're going to put these in brackets to remind ourselves that they're all true at the same time here. All right, so for our electron donating groups, we saw this negative charge being bounced around our ring, meaning that we have this extra electron density in certain positions. For our electron withdrawing groups, we see the exact opposite. Now we have this positive charge being bounced around our ring, which means that when we look at a molecule of benzaldehyde, we want to see on these carbons that relative lack of electron density, that partial positive charge. All right, we have that positive charge on those ortho and para positions in our resonance contributors here, which means that those carbons have a relative lack of electron density. So we have a lack of electron density. And that lack of electron density is specifically at the ortho and para positions. Okay? And also, by analogy of what we talked about before, if we have a group that's taking electron density away from benzene, is that going to make it a better or a worse nucleophile? Now, all of a sudden, it's a worse nucleophile. So these electron withdrawing groups, these are what are called deactivating groups. Right? They make benzene a worse nucleophile. All right, so putting those on a benzene ring will cause it to react slower than if you just had a normal old benzene ring all by itself. All right, and as noted, they're going to make benzene a worse nucleophile, but specifically at which positions are they making benzene a worse nucleophile? The ortho and para, which is why our meta positions are now the only positions available to act as nucleophiles. So whereas electron donating groups were ortho-para directors, our electron withdrawing groups are what are called meta directors. All right, meaning they will direct incoming electrophiles to the meta position. Okay, so when we're combining our EAS reactions, we're going to do our first reaction. Doesn't matter where you put that first group, right? Benzene's all nice and symmetric. You can pick any carbon you want. But then you have to look and you have to decide whether that is an orthopara or a metadirector. And that will dictate where that second reactant goes, where that second electrophile goes. All right? So how do I know that a nitro group is an electron withdrawing group? Let's make a little bit of a master list here. We're going to start with our electron donating groups. And we're going to throw these into buckets. All right, and I'll talk a little bit more about why we make this sort of delineation here, but for right now, you're just going to trust me. This first category, we're going to call our strong activators. These activators are orthoparadirectors. Okay, and a good example of a strong activator would be that phenol group, phenol, that hydroxyl group on phenol. All right, I'm going to put down a few of them, and we're going to take a look and see if we can't sort of see what they have in common here. All right, so what do these all have in common? Yeah, so we got this heteroatom here. The really important feature that this atom has that's going to let you know that it's an orthoparadirector is that it's got a lone pair directly next to that ring. Remember, in order to be an electron donating group, it has to be able to donate a pair of electrons. So if you have a heteroatom with a pair of electrons right next to that ring, that's going to be an electron donating group, an orthoparadirector. All right, we're going to separate these from what we're going to call our moderate activators. All right, still orthoparadirecting. And let's take a look at a few of these and see if we can figure out what they have in common. Okay, it doesn't have to be just one carbon. We can have a bunch of carbons on the back end here. All right, looking at these two groups here, our strong activators versus our moderate activators, what's the difference? We have a carbonyl group. All right, so these also have lone pairs directly next to that ring, right? So they can donate that pair of electrons to the ring. But what do we know about carbonyl groups? They're deactivators because they're electron what? Electron withdrawing groups, right? Which means what? They pull electron density away from themselves. So yes, oxygen, for example, in this molecule, can donate electron density to that ring, but it can also donate its electron density in the other direction, away from that ring, right? So we have that carbonyl group on there, pulling some of that electron density onto itself, which is why these are not quite as good at lending electron density to the ring as our strong activator counterparts, right? Some of that electron density is getting pulled over onto that carbonyl group away from the ring. All right, so now we're going to talk about our weak activators. These are going to look a little bit differently, but they have one common feature. All right, just to note, our weak activators, still ortho-para-directing. All right, what do these all have in common? What are they made of? Carbons and hydrogens, right? So these are just alkyl groups here. Notice that this breaks our trend of having a lone pair directly next to the ring. They still activate a benzene ring, these alkyl groups. All right, but it's this kind of weird quantum mechanical effect called hyperconjugation. And I'm just going to kind of completely punt on this one here. Feel like it's more confusing than it's worth. We're just going to call it a weird quantum effect. You can Google it later if you're curious. All right, and then our last group is kind of the weirdest here in that they are weak deactivators. But even though they're deactivators, they're still ortho-para-directing. And we'll talk about why that is here in a second, but let's just take a look at them. All right, what do these all have in common? Are halogens. All right, so halogens are these weak deactivators, but they're still ortho-para-directors because there's kind of this push-pull going on. They're both withdrawing electron density and donating electron density all at the same time. All right, so first of all, note that they have these lone pairs directly next to the ring, which is our common feature of our activators, or of our ortho-para-directors. And so indeed, they can donate electron density through resonance. Right, just like we showed for all of our other electron donating groups, exception being the alkyl groups, we can use those resonance structures to show that it's donating electron density to the ring. All right, but what we also know about our halogens is that they're electronegative relative to carbon, which means that they're also pulling electron density, but that happens through not resonance, which is occurring through pi bonds, but through the sigma bond here. And this is called induction. All right, so they also withdraw electron density through induction. All right, so that's why these halogens are deactivators, because they're withdrawing electron density through induction, but they're still ortho-para-directors because they're donating electron density through resonance. So they're kind of in this weird category here. All right, if we're going to talk about our other deactivators, these are all going to fall under the umbrella of now being electron donating groups. All right, our first category we're going to look at are our moderate deactivators. These are now going to be metadirectors. All right. And that benzaldehyde example that we looked at is a great example of a moderate deactivator. What's up?
Is this supposed to be withdrawing?
Yes, totally is. Thank you. I'm messing everybody up here. My bad. Yeah, electron withdrawing groups now. We already made our master list of electron donating groups. All right, so let's put down a few of these and see what they have in common. Again, that benzaldehyde's a good example. Oops. All right, just to put down a few more. All right, what do these all have in common? What's directly bonded to that ring? A carbonyl carbon. Right, that's our common feature that we have here. As we established with benzaldehyde, those carbonyl groups are electron withdrawing. If we have a carbonyl carbon bonded to that benzene ring, that would be a moderately deactivating group. There's one more that we're going to add here that's kind of a little bit of an oddball. And this is important to note because we know how to make this one. And that is that sulfonic acid group. And I'm going to draw out the Lewis structure here so we can see why it is still an electron withdrawing group. All right, so at first this seems kind of like an odd man out here because it doesn't have that same pattern of having that carbonyl carbon. But remember, that carbonyl group is good at withdrawing electrons because it can pull this electron away from the ring by bouncing a pair over onto that oxygen. And this sulfonic acid group can do the exact same thing. Right? So our exact same resonance pattern that we saw for our carbonyl groups, we have that for our sulfonic acid group as well because of that double bonded oxygen on our sulfur. All right, and then the last one here are our strong deactivators. Again, these are meta-directors. And this is kind of out of all the other ones I was talking about. Oh, look at all these common structural features that they have. Unfortunately, this category here does not really have the same common thread throughout, but it's a pretty short list. So this is just the list of ones that we got to know here that fall into this category of being strong deactivators. The first one is that nitro group. If you remember, we were first introduced to this in our Diels-Alder lecture as a strong electron withdrawing group. Okay, and I guess I'll do the full Lewis structure just to prove a point here. Okay, again, it can pull electron density away from that ring, just like we saw from our carbonyl groups. But now we have that nitrogen with a positive charge. It's that much stronger at withdrawing electron density. All right, another one that's important to note here because we can make it by taking toluene and adding an excess of that NBS, where we brominate that benzylic position. All right, a fully brominated benzylic carbon here is also a strong deactivator metadirector. All right, and then the last one, we don't really know how to make it, so it's not going to be seen quite as often, but just to sort of have a complete list and note, is this aminium ion here. Okay, so these are now sort of our master list of our electron withdrawing groups here, our metadirectors. So then to go back to that very first example that we looked at and try to understand it based on what we sort of have just established here, go to this first example. Our first reaction was to add a nitro group to this ring. Again, doesn't matter where you put the first one. And then I'm going to look and I'm going to say, all right, a nitro group is what? Orthopara or metadirecting? It is a metadirecting group. So that means it's going to direct incoming substituents to one of those meta positions. All right, which is why when I do my second reaction, my bromine ends up meta to that nitro group. Now, importantly, the bromine didn't get to choose. Right? It wasn't bromine's choice to go to the meta position. It was what was already on the ring that directs the incoming electrophile to a certain position. Right? So what you're adding isn't the one getting to make the decision. It's what's already on the ring that will direct any incoming group to a specific location. All right, so first thing I can ask you with regard to combining these electrophilic aromatic substitution reactions is to follow them, which is basically the example that we just did. All right, so I'm going to put down benzene. I'm then going to give you a list of reagents, and you're going to give me the product of that reaction. Okay, so we got two different examples here. You're going to follow these reactions here, giving me my product. So first you're going to add your first thing to the ring or substitute your hydrogen for the first thing. Then you're going to classify what's on the ring as being an orthopara or a meta-director, and then add the second thing. All right, that's the name of the game here. All right, so if I'm going to break this into these steps here, let's look at step 1 first, and then we'll do step 2. All right, that first reaction is going to add what to the ring, or rather substitute a hydrogen for what? SO3H, right? So what we call a sulfonic acid group, SO3H. All right, so first of all, you can see that having a good command of those 6 EAS reactions is going to be important, right? Because again, we took these 6, we learned them individually at first, and now we're just mixing and matching them. So we need to know what each of them does, right? So again, that's our fuming sulfuric acid, all sulfonic acid group. All right, so then what is our second reaction add to the ring or substitute onto the ring? A chlorine. So I'm going to put a chlorine on the ring next. But I got to know whether to put it in my ortho-para or the meta positions here. All right, does the chlorine get to pick? No, it's what's already on the ring, that sulfonic acid group. So I got to decide what group that falls into. Okay, is this an ortho-para or a meta-director? Meta-director, that's our sulfonic acid group. I wrote it in that condensed form down there. That's our sulfonic acid group. So this is a meta-director, which means I'm going to put the chlorine on one of these meta positions here. All right, so that's the name of the game here. I want everybody to take a second, given what we just discussed, try to do that last one. Okay, I picked 2 different EAS reactions. Treat it the same way. If you need to break it up into those individual steps, then do that. All right, at some point you'll probably be able to shortcut it, but while you're starting out, just break it up into those individual steps. Okay, these are these Friedel-Crafts reactions. The first one is a Friedel-Crafts alkylation reaction. I'm going to be putting this alkyl group on my ring since I'm using a 2-carbon alkyl halide. That means I need a 2-carbon alkyl group on here, an ethyl group. And then the second reaction I'm going to follow it up with is now an Friedel-Crafts acylation reaction. All right, so I'm going to be sticking this acyl group here on the ring, specifically bonding the benzene carbon to my carbonyl carbon. All right, but before I can do that, I got to figure out where it's going to go. Is this alkyl group an orthopara or a meta-director? Orthopara. Which means I'm going to get a mix of that acyl group being directed to the ortho position and to the para position. All right, so we would draw both a product with that acyl group on our ortho position and that acyl group on our para position. All right, so we get a mix of that ortho and that para product. Which one do we think we would get more of? The ortho or the para? The para. Why the para? Because those big groups are further apart, right? There are some examples where you actually have more ortho positions. You have 2 of them. So there are some examples, specifically if this thing is really tiny on the ring, where you would get more ortho product, but 99% of the time, the para product is our major product. All right, because of our fancy word for big groups like to be far apart is what we call steric hindrance. Cool. So I could ask you to follow these EAS reactions. I give you a list of reactions, and you have to give me what the product is, having done those reactions in that specific order. All right. The other thing that I can ask you to do, though, is to find your own synthesis pathway here by telling you, all right, we're going to start with benzene, and I want you to make a specific benzene derivative. And you got to tell me how to do it. How do we get from reactant to product here? What reactions do we do, and in what order do we do them in order to create this specific product? If you do this first, that's going to be what, an orthopara or a meta-director? You got lone pairs next to the ring?
Wait, no, oh, this would be meta.
No. Lone pairs next to the ring, orthopara.
Yeah. So we can't.
Yep.
Oh my god.
No, because the halogen's the ortho-para director, and you need them to be meta to one another.
Is this
So
one
you're going to have to do
on?
your acylation first to make sure that that incoming chlorine goes to the met. Yeah, exactly. Okay, so how am I going to do this? I'm going to first make note of what I would need to do in order to add these two groups or substitute these two groups, right? So to add chlorine to the ring, we use chlorine, aluminum chloride or iron 3 chloride. To add this acyl group to the ring, I'm going to need to use, in this case, a 3-carbon acyl chloride and aluminum chloride. So step one, I got to know what reactions to use. So these are my two reactions. Now I got to figure out what order to use them in. So I'm going to note here, chlorine is what? An orthopara or a meta-director? Orthopara. Let me just note here, all of our orthopara directing groups have this common feature of having that lone pair directly next to the ring, with the exception of our alkyls. So that's what we got to be able to spy for orthopara directors. Is there a lone pair right next to the ring, or is it an alkyl group? If either of those are true, it's going to be an orthopara director. All right? So in this case here, my chlorine is orthopara. All right, and this acyl group with its carbonyl carbon bonded to the ring is meta-directing. And then I got to look here, in my ring, in my product, are these sitting orthopara or meta to one another? Meta, which means I need to do that meta-directing reaction first. I'm going to have to first do that acylation reaction to add that meta-director onto the ring. All right, and then I can do my chlorination reaction, because that will then direct that chlorine to that meta position. All right, so remember, the thing you stick on the ring first is going to direct the next reaction to a specific location. So if I'm going to have a product that's meta, I need to do this meta-directing reaction first, right? Or rather, substituting a meta-director onto that ring first. All right, so obviously, like again, these 6 electrophilic aromatic substitution reactions are going to be really important, right? Because we're just mixing and matching them. There are 4 other reactions that are going to come into play here that are also going to be very important for this particular section. They are not electrophilic aromatic substitution reactions, but rather reactions that happen to stuff already on the ring. And why these are going to be important and why we're going to throw these in our separate category here is because these are reactions that convert orthopara directors into meta-directors and vice versa. I know, very exciting. Okay. All right, so in our previous chapter, we tacked on these 2 reactions at the end, these reactions at the benzylic position. So let's take a look at that again. If we take toluene and react it with a large excess of NBS, what was NBS doing for us? Brominating that allylic position, and if we have a crap ton of excess NBS, we're going to completely brominate that benzylic position. Okay, and again, we want to make special note of this here because toluene, with its methyl group, is what? Orthopara or meta-directing? Orthopara. Our alkyl groups are orthopara directors. All right, but what about when I have this fully brominated benzylic carbon? This is a meta-director. Notice that the lone pair is not directly next to the ring, right? So I'm not lying to you about that lone pair next to the ring business. It's not directly next to the ring. It's bonded to that carbon. These were one of our strong meta-directors here. Okay. We could also take that toluene we already established is an ortho-para-director, and we could do that oxidation reaction. So we had two oxidation agents that we looked at, potassium permanganate and sodium dichromate. Sodium dichromate you have to use under these acidic conditions. All right, these both oxidized that benzylic position, creating what functional group? Carboxylic acid. Yep. So remember, oxidation in organic chemistry, we mean we're creating more carbon-oxygen bonds. All right, so we replace all those hydrogens on that methyl group with oxygen bonds. Okay, and then a carboxylic acid would be considered what? Orthopara or meta-directing? Meta-directing. Right, carbonyl carbon bonded to that ring. Okay, so these two reactions that we learned at the benzylic position, they're going to come into play in this business that we're doing, combining these AAS reactions, because they can flip an ortho-para-director into a meta-director. All right, we're going to learn two new ones. Okay, these are then going to fall under the umbrella of reduction reactions. So oxidation in organic chemistry is creating more carbon-oxygen bonds. Reduction is creating more carbon-hydrogen bonds. All right, and we can take one of those acyl groups and we can reduce it, effectively chopping off that carbonyl oxygen, replacing it with a bunch of hydrogens. All right, there's a few different reducing agents that you can use, specifically like looking at the one in our book. I'll say a lot of them, they have this common feature of using transition metals. Transition metals are great at facilitating transfers of electrons, which you need for oxidation reduction reactions. All right, and zinc is one in particular that's great at helping to reduce carbons. All right, and this is important to note here because this acyl group with its carbonyl carbon bonded to the ring is a meta-director, but that alkyl group, an ortho-para-director. All right. And then our last one here, also a reduction reaction, but reducing a nitrogen from being fully oxidized as a nitro group into aniline. Okay, this reduction reaction also requires zinc under acidic conditions, but then has this follow-up step using sodium hydroxide. All right, and again, of note that nitro group is our strong meta-director, but aniline with that lone pair right next to the ring is an ortho-para-director. All right, so these are not electrophilic aromatic substitution reactions. We're not adding anything new onto the ring here or substituting a hydrogen for anything new, but we are converting what's already on the ring from being an ortho-para director to a meta-director or vice versa. So they're going to come into play in this whole combining of our EAS reactions. All right, so let's do some examples here. One where you're going to be following and the other one where you're going to be predicting your reaction pathway.
Oh my god, bro.
So you have to be careful because this second reaction doesn't add an aniline to the ring. It converts the nitro to an aniline. So you're not going to have both. You're going to swap that for now an aniline.
Wait, no, nitro, isn't it a nitro group, not NH2?
Sodium hydroxide, both of those together, if you scroll up real quick to your list of those four that we were looking at, both of them combined in two separate steps are what does that conversion.
Oh, both of them, they're both included.
They're both included. You need to do them in separate steps. That's why they're listed that way. The very first one? So there were two different reducing agents that looked very similar. Both had involved zinc and HCl. For the nitro group, it was this two-step process here. The heat was the other reduction reaction, reducing the carbonyl group to just an alcohol. This is, yeah, so there were two separate, that should be separate.
I'm sorry.
Notice how it's listed in these two steps, which is why it's broken into two steps here. It could happen actually. Yep, and it would dictate what your product was. So for example, if I swapped 2 and 3 and that last step there, I would get a different product switches.
And then that will be alcohol group and then KOH.
No, so note that these two, both steps are involved in that reducing.
Oh,
So if you go to your
okay,
list here, you got to do it in two separate steps,
Oh, okay,
which is why
okay.
they're listed that way in that reaction.
Okay, and then the last will be the sulfonic acid.
Yep.
The orthopara.
Yep.
Okay, wait, I got to the
So one is add the
nitro.
2 and 3 are
It's
converting
to
to
the amine.
orthopara. And then it's add the sulfonic
Totally.
acid.
So maybe we should look at our list of reactions up here that will flip
So now that you're saying
orthopara and metareactors. Yeah,
So
see if you can use any one of those
okay, so
to
then
help you solve that problem.
Is what orthoparas and then oh wait.
So because we do this 2 and 3 here, that flips it to a amine group. This is no longer a meta director though. This one here is now an orthopara director. If we had done this, like this would be correct. If you
Isn't it like
swapped steps 2 and 3 and
something?
step 4, then you would get this product here. But since we did 2 and 3 in the middle, we converted that from an orthopara to a meta director. And this is awesome. The only thing I have is just be careful. These reducing agents are very similar. It's different for the nitro group than it is for that acyl group.
So
The acyl
one's
group also
ortho and
uses
then
zinc
one's
HCl, but then
counting.
heat,
Yes.
there's no second step of anyone. Alright, but this is exactly right. Yeah, that's up.
So that's what's going on there.
Because you know how they're like orthoparas, so they can be like either.
You just mix the other.
I think. I don't know. I feel like they want to I think I got it.
It should be an orthopara.
Yeah, and you can't get rid of those bromines with that.
HSO3.
So what's in our product?
I wanted to draw it, but I gotta.
It's SO3H.
Obviously, there's like last step.
I don't know what the first one.
So be careful. You're telling me orthopara.
So the other things in ethyl and alcohol.
Trying to figure out. Okay.
So this did you draw?
Okay, so do you want to know how it's, yeah, it's S, no, it's S with the two double bonded oxygens and an OH.
You're close. You're
Oh, I had
definitely
it right.
going to need to utilize
Okay,
one of
you
those.
still have the
it'll
video
be
going
fine.
on.
So we have to say
There you
before
go.
you convert to the meta, right? Because they're both orthopara, right?
They are, which means you don't want to, you can't convert them into a meta director. You need to convert a meta director
not see the
into
next
them,
one.
into one of those, since that's
Oh,
the
that makes
product.
sense, okay.
So,
When I do this right.
that looks great. Yep.
Yay.
And Bronos is in mine.
Just be careful. The H is bonded to the oxygen in that
Oh,
molecule,
yeah,
so SO3H is how we would list it.
Okay.
I'll have it.
Okay.
So you can add the.
Yep. Yes, exactly. The heat isn't in an extra step. That's not really a big deal at all, but yeah. Okay, real quick, I dilly-dallied around, ran out of time here. Importantly, this first reaction, I'm just kind of do this quick. First reaction, we'll put a nitro group on that ring. All right, our second and third reaction, these two steps combined are that method for reducing a nitro group. Notice how it's broken into two steps here. You got to do them separately. So that's why it's written that way in our list here. So my nitro group is no longer a nitro group. It's going to become an aniline. All right, and unlike my nitro group, aniline with that lone pair right next to the ring is an ortho-para director. So that means any incoming substituent is going to be directed to the ortho or para position. So when I do that last reaction, I'm going to add that sulfonic acid group. I'm going to get a mixture of it being added to the ortho position and it being added to the para position. Squeeze this in here. All right, so now for this one here, this is a tricky one. Because you're going to look and you're going to say, all right, I know how to add this thing to the ring using my bromination reaction, and I know how to add this thing to the ring using my Friedel-Crafts alkylation reaction. The problem is that a bromo group is an I'm just going to say OP, an ortho-para-director, and an alkyl group is an ortho-para-director. And yet in this product here, they are sitting meta to one another. All right, so how am I going to rectify this? Well, what we're going to have to do is we're going to have to take advantage of our reactions here that convert ortho-para to meta-directors and vice versa. All right? What we can note is that, yes, we can put an alkyl group on that ring by doing a Friedel-Crafts alkylation reaction, but we could also instead do a Friedel-Crafts acylation reaction and then reduce that acyl group into an alkyl group. All right, and by doing that acylation reaction first, we've added a meta-director to the ring. Okay, so first, how many carbons I got on there? 2. Okay, now I don't want to reduce it yet because I need its meta-directing powers. So I'm going to then do my bromination reaction. And once that bromine's on the ring, then I can reduce that alkyl group using that zinc, HCl, and heat. Cool. All right, we are going to, I'm going to complicate things a little bit next class period, but also we're just going to do a lot of practice, all right? So you can maybe see where this is going. We have yet to factor in the strong, moderate, and weak business, all right? So we'll talk about that next class period, but we're just going to practice these reactions kind of over and over and over again, okay? Practice makes perfect for this particular topic. Cool. All right, we'll start lab 5 minutes late here.